I think that the word proper water is related
we're also time. So our afternoon session is sequential decision making, and Weinberg of Princeton.
Great, thanks. So similar to Kamesh's first talk this morning, both of the talks are going to be more like class lecture style. So we are going to see some complete proofs, but not necessarily a survey of many different results in this area. Okay, so the kinds of problems we're going to study are online selection problems. So the kinds of problems we're thinking about are, imagine you're trying to hire a secretary or find a job or select a life partner or something that presumably you only want one of. And so how you might model this is that at every time step, a secretary is going to arrive. You're going to interview the secretary and learn their value. And then you have to immediately and irrevocably decide whether or not you want to hire them. Okay, and the reason this is hard is because you can only hire one secretary. Okay, so just what a sample run might look like is good. So at time step 1, Bulbasaur arrives, and you decide, I don't have enough information yet, so you decide not to hire him, but you lose him forever. And then at time step 2, Squirtle arrives, and you also decide that you're not happy with Squirtle, so when you decide not to hire, you lose it forever. And then at time step 3, Charmander comes, and you decide this is okay, and you decide to hire Charmander, but you don't get to see what else is going to come in the future. Okay, so let me, before going into these two specific models, describe an impossible problem for you. Okay, so let's say that we decide to model this mathematically in the following way. So offline, every secretary is going to be assigned a weight by some adversary, and these weights are unknown to you. And then the adversary is also going to choose an ordering of the elements. Okay, and then online, the secretaries are revealed to you one at a time, and you learn their weight. You immediately and irrevocably decide whether or not to hire them. And your goal is to maximize the probability of selecting the max weight element. Okay, and so it's not too hard to see that if this is the model you're working in, then the best thing you can do is just hire a random secretary. And so the point is that we don't actually learn anything about what are good algorithms to do online selection problems. So we have to change something. One way to change the model is to take away the adversary's power to choose an ordering. Okay, so maybe the adversary still chooses the weights, but the secretaries are permuted randomly before they're revealed. Okay, so this is called the secretary problem. And so here but online it's the same. The secretaries are revealed one at a time. You learn their weight. You immediately and irrevocably decide whether or not to hire, and your goal is to maximize the probability of selecting the max weight element. Okay, so just to be clear, a sample run that might happen is here the adversary has assigned these weights to the secretaries. And then at time step 1, Charmander comes, and maybe you decide that you don't want to hire, so you throw him away. And then at time step 2, Bulbasaur comes, and you decide he's definitely not the max weight element because he's not even as large as the best we've seen so far. And then maybe at time step 3, Pikachu comes, and you decide that he's better than everything you've seen so far, so this is good. Okay, and then the point is still you don't get to see what would have come in the future had you continued. Okay, so secretary problems are what we're going to study in the second half. What we're going to study in this half are called profit inequalities. Okay, so here basically the role of the randomization and the adversary are switched. So what's going to happen offline now is that every secretary has a weight drawn independently from some distribution. And the adversary gets to choose the distributions and the ordering, but the distributions are known to you. Okay, so that's where you get some randomness. Okay, and online it's exactly the same. The secretaries are revealed one at a time. You immediately and irrevocably decide whether or not to hire. And now your goal is to maximize the expected weight of the selected element. Okay, so again, just to be clear, here's one sample run. So maybe in this instance, the weights are drawn from these different uniform distributions. And in time step 1, Bulbasaur will be interviewed, and you'll learn that his weight is 5. And you'll decide that's not good enough. You think you can do better in the future.
So is there a cost in seeing more and more candidates?
There is no cost to see more candidates, but the only way you get to see more candidates is if you don't hire anyone. So the cost is that you don't get to go back at the candidates who were better before.
Is it a finite sequence?
For this talk, yeah, it's going to be a finite sequence.
So you know how long the sequence
And let's also say for this talk, you know how long the sequence is. So you know you know how many elements there are, and you know all the distributions associated with them.
So you know the correct permutation of the distributions? You know the first one is...
You know let's even say you know the correct one. Yes, I'll very briefly at the end touch on you can change these assumptions to say what if you don't know, what if the adversary gets to change the ordering adaptively, and some of the results that I'm going to present hold in those models too. Yeah. Are there any other questions? Okay. Okay, good. So again, going through this example, after you decide to turn down Bulbasaur, then you interview Squirtle, and his value is 7, and you decide, you know what, I think 7 is better than what I can get if I continue interviewing. So you take Squirtle, and once you decide to do this, you no longer get to see what weights actually would have come from the secretaries in the future. Okay? So after this, is the problem clear? So I'm going to dive straight into some analysis now. Okay, so the first thing that I want to observe is that we can find the optimal policy using backwards induction. Okay, so let's see what that looks like. So if somehow we find ourselves making it all the way to Mewtwo without having hired a secretary, then definitely we should hire him, right? Because there's nothing we can possibly gain by waiting. Okay, so if we make it all the way to Mewtwo, we will hire him and we'll get 4.5 in expectation. Okay, so now we can reason if for some reason we find ourselves making it all the way to Pikachu, we have two choices. We can either reject Pikachu, and if we do that, then we'll get 4.5 in expectation from Mewtwo, or we can accept and we can get Pikachu's weight. Okay, so the best decision at this point is to accept if Pikachu's weight exceeds 4.5. Okay, we can go back one more step and say, okay, now if somehow we find ourselves making it to Charmander, we can either reject and run the optimal policy starting from Pikachu, which gets 4.625 in expectation, or we can accept and get Charmander's weight. Okay, so we should accept only if Charmander's weight exceeds 4.625. In this example, it never will, so you will always reject him. And you can see how to continue this reasoning all the way back to Bulbasaur. And this will tell you exactly what the optimal policy is. It's just a sequence of different thresholds for each secretary. You should hire if they exceed their threshold and reject otherwise.
So in contrast to the regular secretary program where your goal is to maximize the probability of choosing the maximum, here you don't.
Here we want to maximize the expected weight of what we select. Yeah, so the objective is a little bit different.
Where did you get the 4.65?
So this is conditioned on starting from Pikachu. If you run this policy, I'm just claiming it will happen to be 4.625. Yeah. Okay, sorry, so let me go back. So we know what the optimal policy is. And so what questions do we still study? Well, just because we know what the optimal policy is doesn't mean we know how well it does. Okay, so that's the first question, and this is kind of asking for a competitive analysis. So how well does this policy do when compared to a prophet? So by a prophet, I mean someone who knows all of the weights every time they're sampled and always picks the max weight element. Okay, so specifically, does there exist some number C such that for all instances, the gambler can get a C fraction of the prophet's expected reward? And the second question is this dynamic program told us to set different thresholds for each element. It's a reasonable question to ask, is it possible to get the same competitive ratio by just setting a single threshold for all the elements? Okay, and so here the main theorem is due to seminal work of Krengel and Suchestin and follow-up by Samuel Kahn, which shows that there is actually a uniform threshold that guarantees half of the prophet's reward and expectation, and this is the best competitive ratio possible. Okay, so I'm not claiming that the uniform threshold is always optimal, because the dynamic program will often tell you to use different thresholds, but if you just care about competitive ratio, then a half is the best you can get, and you can get that with a uniform threshold. Okay, so so I'm going to give you a complete proof of this, but let me show you what the tight example is first. Okay, so in this example, there are only two secretaries. The Bulbasaur shows up first, and his weight is deterministically 1. And Squirtle shows up second, and his weight is 0 with probability almost 1, and 1 over epsilon with probability epsilon. Okay, so now let's reason, what does the profit get on this example? Well, they get 1 over epsilon whenever Squirtle's value is high, and they get 1 whenever Squirtle's value is 0. So they get 2 minus epsilon. And now what about the gambler? The gambler has two choices. He can either accept Bulbasaur, and then he gets 1 for sure, or he can reject Bulbasaur without knowing Squirtle's value. So at the time he decides to reject Bulbasaur and take Squirtle, all he knows is that Squirtle's value is drawn from this distribution, which has an expectation of 1. Okay, so no matter what the gambler does, he can't do better than 1. Okay, so that's a tight example. Let me now prove this. Okay, so the threshold we want to use is exactly the expected reward of the profit over 2. So the expected max weight element divided by 2. And we're going to accept the first element that exceeds this threshold. Okay, some notation for the proof. I'm going to use P to denote the probability that the max weight element exceeds our threshold. And I'll use this alg sub I to denote the contribution of element I to the algorithm. So this is the weight of element I times the indicator that we accepted. Okay, and also just for cleanliness, I'll use this notation x plus to be the max of a random variable x in 0. Okay, so I'm going to show you a complete proof. The math is somewhat pedantic, but I do want to go through the whole thing.
And the distributions of the different ones are different.
The distributions of the different ones could be different. Yes.
But you didn't need to know the permutation here.
You did not need, correct. You did not need to know the permutation to decide this threshold. That's right. Okay, so this first line is straightforward. So what are we going to do? We're going to decompose the expected reward of the algorithm to just sum over every element, the expected contribution of the element to the algorithm. And then all we're going to do is we're going to take alg I and we'll break up wi into wi minus t and plus t. Okay, so for the second line, we'll observe that t is a constant. So the expected value of t times summing over all I, the expected value of this indicator that the algorithm accepts I, is just going to give us t times the probability that the algorithm accepts something. Okay, so now we want to think, what is the probability that the algorithm accepts something? Well, if one of the elements has weight larger than t, the algorithm will accept something. And if the max is less than t, the algorithm will not accept anything. Okay, so this probability is exactly p. Going to the next line, we're just going to process what does it mean for the algorithm to accept I? What has to happen? Well, wi needs to exceed the threshold, and we need to have not accepted anything before we got to element I. Next, we're just going to observe that this indicator, that wi is larger than t, if it's the case that this is negative, this indicator will be 0. If it's the case that this is positive, the indicator will be 1. So this indicator times wi minus t is just wi minus t plus. The max of wi minus t was 0. The next step, we're just going to observe that whether or not you accept any element before I is independent of wi, because it only has to do with the weights that come before. So I'm just going to replace this indicator inside the expectation with a probability. And the last step is we need to understand what is this probability. Well, it's at least 1 minus p. So why is this? The probability that the algorithm accepts anything in the entire run is 1 minus p. So the probability that it accepts something before it reaches I is, the probability that it doesn't accept anything in the entire run is 1 minus p. So the probability that it hasn't accepted anything by the time it reaches I is at least 1 minus p. Okay, so this is not the proof yet, but this is the first step. So we've observed that the expected performance of the algorithm is at least p times our threshold t plus 1 minus p times this sum, which I'll refer to as the surplus. So this is kind of like the expected sum of the weights beyond what the threshold itself gets. Okay, and I also want to point out we didn't actually use the choice of threshold in this part of the proof yet. Okay, so this holds for any choice of threshold, you can get this guarantee. Okay, so that's step 1. The other thing we need to do now, we need to use this and try and bound the expected max. Okay, so let's do this. So this is again going to be pretty pedantic, but we'll start by just upper bounding the expected max by taking the max minus t and plus t. Okay, the expected value of t is exactly t. And this max over all weights minus t, this is the same thing as the max over all weights of wi minus t. Okay. The next step, we'll just observe this is a max over all non-negative terms. So we can upper bound the max with a sum. And now the last step is observe that we've just shown that the expected max is upper bounded by this term t plus the surplus. So that means that the expected surplus is at least the expected max minus t, but our choice of t was exactly the expected max over 2. So that means that the expected surplus is also at least the expected max over 2. Okay, so what that tells us is that both our choice of threshold t is at least the expected max over 2, and this expected surplus term is at least the expected max over 2. And so combined with the fact, so the reward of the algorithm is p times something that's at least the expected max over 2 plus 1 minus p times something that's at least the expected max over 2. So we get at least the expected max over 2. Okay, so I want to give a little bit of intuition for what happened here, but are there any questions about this?
There is a non-zero probability that you would accept nothing, which you can.
There is a correct, yeah. So it's definitely there's no way this is the optimal algorithm for any instance. But if you just care about the competitive ratio, it does get you the optimal competitive ratio. Yeah. Does that make sense?
Yeah. But you can compute the probability that you won't accept anybody, and if that probability is high, you can do something about it.
Correct. You could do something more clever, but the point is that if you choose to do something more clever, on many instances it might help you. But if you only care about the worst case approximation ratio, then it's not going to do better than 2. Yeah. But in practice, of course, you should do something better than reject everything. Was there another? Okay. Okay. So so what just happened? So this being able to lower bound what you get with p times a threshold plus 1 minus p times a surplus, this holds for any choice of threshold. Okay, but b is what let us get mileage out of a, and the point is that we have no control over the value of p. So if we want to get a good bound from this observation, then we need both of these terms to be large. So I'd like to say that kind of what happened was that this threshold was not too big, so that the expected surplus, that what we get above the threshold, was still pretty large. But it was also not too small in the sense that the threshold itself contributed a good fraction of the expected max. Okay, so what happened was that this threshold, I would say, is balanced. And this isn't a formal definition yet, but we are going to see this idea more throughout the talk. Okay? Okay, so what we just saw was a simple description of the optimal stopping rule. And we saw a tight competitive analysis that happened to also be achieved by a uniform threshold. Okay, and so what we're going to do in the rest of the talk is we'll look at harder versions of this problem. So what if you have multiple choices? Okay, so what I mean by that is that still every secretary will have a weight drawn independently from some distribution that's known to you. Now the adversary will choose these distributions and the ordering, and also some feasibility constraints on which secretaries you can simultaneously hire. And I'll give you some examples on the next slide. Okay, but these feasibility constraints are also known to you. So now what happens online, the secretaries are still revealed one at a time. You still immediately and irrevocably decide whether or not to hire. But now instead of only being allowed to hire one secretary, it must be the case that the set of secretaries you've hired so far has to be feasible at all times. Okay, and your goal is to maximize the expected sum of weights from the secretaries you hire. Okay, let me just give you some examples of what these feasibility constraints might look like. So maybe you're trying to fill k positions, and it's feasible for you to hire any set of k secretaries. Okay, or maybe you associate to every secretary an edge in a graph, and it's feasible for you to hire any acyclic subgraph. Or maybe you associate each secretary with a vector in a vector space, and it's feasible for you to hire any linearly independent subset. Okay, or maybe you associate each secretary with an edge in a bipartite graph, and it's feasible to hire any matching. Okay, so these are just examples of what these feasibility constraints might look like. So what I want to accomplish with this slide, I'm not going to read through these results. This is mostly just to convince you that our community has done a lot of work recently on designing multiple choice profit inequalities. I'll leave it up for a minute in case you want to read through the results. You can ask me questions. But while you're reading it, I'll just define for you two terms. The first is a matroid. So I would say that feasibility constraints form a matroid if it has the following two properties. So first, the feasibility constraint should be downwards closed, meaning that every subset of a feasible set is also feasible. And second, it has this property such that whenever you have two feasible sets, and one is larger than the other, there is always some element of the larger set that you can add to the smaller set and maintain feasibility. Okay, so I think many of you are probably comfortable with this, but just in case you're not, you can think of feasible sets as roughly corresponding to linearly independent vectors in a vector space. Okay, and matroid intersection is if you give me a list of matroids and say that a set is feasible if and only if it's feasible in every matroid separately. Okay, so for instance, we know that we can write bipartite matchings as an intersection of two matroids. We can write 3D matchings as an intersection of three matroids. Okay, so again, so I'm not gonna talk in much detail about most of these results. But what I want to do in the rest of the talk is continue kind of hammering in this concept of balanced thresholds. And I'll do this first by giving you a formal definition, and then showing you how to use this definition to get a 2 approximation for k-uniform matroids, and also a 2 approximation for arbitrary matroids. Okay, and just remember the high-level idea is we want to come up with thresholds that are big enough so that the thresholds themselves contribute high weight, but also small enough so that the expected surplus beyond these thresholds is still high. Okay, so now let me get into the first part. So I'm going to try and provide for you a formal definition of what it means for thresholds to be balanced. Okay, and to do this, I need to introduce 1 or 2 slides of notation. So let me get started with that. So I'm just going to use opt to denote the max weight feasible set. And all I want to emphasize here, just to be really clear, is that the max weight feasible set depends on the weights of the elements. Okay, so for different weights of the elements, the max weight feasible set will change, and so will its weight. Okay, I will introduce this term called the remainder of a set H with respect to some weights is the following. Let me read the English first. This is the best subset of opt that we could have added to H and still remained feasible. Okay, so formally, this is the argmax over all subsets of opt such that S union H is still feasible of the sum of the weights in S. Okay, and I'll give some examples in pictures after this so you can see what this looks like. And I'll define the cost to be everything in opt that is not in the remainder. Okay, so you can think of this as what we lose from opt by accepting H. Okay, and just to give you a heads up, I am going to abuse notation for the rest of the talk. I will use these 3 terms to denote these 3 sets, but I'll also use them to denote their weight. So I'm going to write things like the expected opt and the expected remainder. What I mean is the expected weight of these sets. Okay, so let's see just some examples to try and make these definitions clear. Okay, so let's say that sets of size 1 are feasible, and here are the elements, and here are their weights. Then opt is mu2. And what's the remainder of Charmander? So this is the best element of opt that we can add to Charmander and still be feasible. Okay, but we can't add anything to a set of size 1 and still be feasible because the feasibility constraints are only sets of size 1. Okay, so this means we can't actually add anything from opt to Charmander, so the remainder is the empty set, and the cost is everything else. So think of this as by accepting Charmander, we can no longer accept mu2. Okay, if instead we start from the empty set, the remainder is mu2 because we can add mu2 to the empty set and still be feasible. And the cost is nothing because we don't lose anything from opt by accepting nothing. Okay, if instead sets of size 2 are feasible, then opt is now Pikachu and mu2. Okay, so what's the remainder of Charmander? So again, it's the best subset of opt that we can add to Charmander and still be feasible. So that's mu2 because this is the max weight subset of size 1. So what is the cost of Charmander? It's everything else. So this is Pikachu. And how you should think of this is that by accepting Charmander, we can still accept Mewtwo, but we can't also accept Pikachu. So that's the cost. Okay, similarly for the empty set, the remainder is Mewtwo and Pikachu. We can still add both of them and be feasible, and the cost is nothing. And if I have a set of size 2, Bulbasaur and Squirtle, then the remainder is the empty set. We cannot add anything to them and still be feasible, so the cost is the entire opt. Okay, so in general, if sets of size k are feasible, so if it's a k-uniform matroid, then the remainder of a set H is the top k minus h elements of opt, because these we can still add to H and be feasible. And the cost are the lowest H elements of the top k, because once we accept a set of size H, we can still get the top k minus h elements, but we can't also get the lowest H. Okay, let me do one more example that's a little bit more combinatorial, and then I'll move on from the definitions. Okay, so here's a example of a graphic matroid. So feasible sets are acyclic subgraphs. Okay, so in this example, what is opt? It's the 3 black edges, E, D, and C. And so we can ask, what is the remainder of A? So it's the max weight subset of E, D, C that we can add to A and still not have a cycle. Okay, so we can't add both E and D to A because we would get a cycle. So the max weight subset we can add is E and C. So this is the remainder, and the cost is D. Okay, similarly, if we start with the element E, then we can't add E because that would create a cycle if we have 2 copies of the same edge. So the remainder is D and C, and the cost is E. And the remainder of this set AB is E, because we can still add E and be feasible, and that causes us to lose D and C.
Sorry, if you say that the cost of E is equal to E, shouldn't you also say that the cost of A is also A as well as D?
No, because A is not in the max weight basis. Yeah, so it's a property. It's always elements of opt are the only ones. Yeah. Okay. Are there any, so this is the last. So I'm going to move on from the definitions. Anyone else have other questions?
So if opt is not unique, then you have some problem.
Let's assume that all the weights are distinct, so that opt is unique. Yeah. Okay. Okay. Okay, so the last one. So let me just formally define what is a thresholding algorithm. It just defines a threshold for every element I, and maybe these thresholds depend on the weights of the previous elements. Okay, so we haven't seen examples of this yet, but if you're running an algorithm, you could set a higher or lower threshold for element I depending on the weights you saw so far. Okay, and so I'm not going to write this the whole time, but just remember that thresholds can depend on earlier elements. Okay, so now here is a formal definition of what it means for thresholds to be balanced. Okay, so a thresholding algorithm has alpha balanced thresholds if, whenever it accepts a set H, we have the following 2 guarantees. So first, the thresholds are not too small in the sense that the sum of the thresholds for all the elements we accepted themselves cover a 1 over alpha fraction of the expected cost. And also, the thresholds are not too big in the sense that the sum of the thresholds for any, let me say this first, for any set V that we could have added to H and still been feasible, the sum of the thresholds we used to reject the elements in V is at most 1 minus 1 over alpha times the expected remainder. Okay, and just to be clear, when I say the expected cost and the expected remainder, I mean with respect to fresh samples drawn from the distributions, completely independent from the weights used to select H. Okay, so again, I want to give you a couple pictures just to make sure that the definition is clear. Okay, so what do I mean when I say the expected cost and the expected remainder? So in this example, everyone's weights are drawn uniformly from the interval 0, 1. And we'll say sets of size 1 are feasible. So the expected max weight element is 5, 6, because there are 5 elements. Okay, so what is the expected remainder? Is there a question? Okay, so what is the expected remainder of Charmander? So we said the remainder of Charmander is the empty set. So the expected weight of the empty set is 0. And what's the expected cost of Charmander? It's the expected weight of the max weight element, because that's the cost of Charmander. So it's going to be 5, 6. Okay, and again, so what's the expected remainder of the empty? Yeah.
But what happens if Charmander is the highest cost?
Right. So that's good. So that's why I mean. So when I said this is the expectation is with respect to fresh samples, completely fresh. Okay, so what I mean is, so formally what I mean is that Charmander for every time I sample the weights, Charmander will have some cost and remainder, and I want to take the expectation over resampling. So maybe Charmander winds up being the remainder of itself, but I would take Charmander's weight in that case.
So your TI depends only on the weight seen so far, not
Correct.
on how much room there is in.
Okay, so that's a good question. So let me go back. So so I'm claiming that if you know how you set the thresholds for the previous weights, then you also know how much room there is left. So all the information you really need are these weights, but in principle, you're also using this information because you will know what you accepted in the past. Yeah. Okay, and similarly, when we talk about the expected remainder and cost of the empty set, the remainder of the empty set is the max weight element. So this is the expected weight of the max weight element. And the cost of the empty set is the empty set, so this is the expected weight of the empty set.
So I'm getting a bit confused. Opt is not a deterministic thingy here.
Correct.
So how do you define the cost and remainder? If
Correct. So opt is a random variable that is the max weight element. So here I'm saying so what I mean formally by this is the set Charmander is fixed. Then I randomly sample weights. I see what is opt. Then I partition opt into cost and remainder, and I take the expected weight of this. Okay. Yeah. So I'm trying hard to draw this connection between, we know that the expected opt is 5, 6, and so this is why we see 5, 6 here. It's because for every samples we're recomputing opt and we're recomputing the cost and remainder. Okay. So again, let's see. So what happens when sets of size 2 are feasible? Then the expected opt is 5, 6 plus 2/3, the expected weight of the highest plus the expected weight of the second highest. Okay, and let's go through the same reasoning. So if we have a set of size 1, the remainder is the max weight element. So the expected remainder of Charmander is 5, 6. And the cost of Charmander is the second highest element. And the expected weight of the second highest element is 2/3. Okay, and then similarly, the remainder of the empty set is the entire opt, which has expected weight 3/2, and the cost is 0. And again, if we start with a set of size 2, the remainder is the empty set, so the expected weight is 0. And then here, the cost is the entire opt, so the expected weight is 3/2. Okay, so in general, if you have feasibility that is sets of size k, then the expected remainder of H is the expected weight of the top k minus h elements, and the expected cost of H is the expected weight of the lowest h elements from the top k. Okay, and again, this top k and the lowest h of the top k, these are chosen after you sample the weights. Okay, so actually are there any questions about, yes?
So maybe it's moving away a little bit from what you want to do, but it seems like a good property of an algorithm would be that if the weights are IID, then the competitive ratio should go to 1. And those thresholds will never do that.
So I think if the weights are, oh, you mean if you have more and more elements? That's true. So I'm not claiming that this is the best thing to do. I'm just claiming that if your goal is to get the optimal competitive ratio for non-IID examples, then this gets you the optimal competitive ratio. So I'm not claiming anything beyond that. Yeah. So in particular, it doesn't have the property you just said. And I'm not claiming that's an undesirable property. I'm just claiming I'm focusing just on getting the optimal competitive ratio and nothing else. Does that answer your question or not?
Trying to find motivation to focus on those strategies. It seems like it's going to be nice because it will be easier to analyze, but on the other hand, you lose a lot.
Yeah, so I would say it gives you two things. One is it does give you a lower bound on how bad the optimal policy can be. So that's one. So that's, I think, the original motivation for doing this analysis was to understand what is a competitive ratio of the optimal policy. The other thing it gives you is at least gives you something you can do in the event that it's difficult to find something better. So let me just be clear, I'm not pushing this as when you're faced with this problem, this is exactly what you should do. But I do think it's still worth, I do think it's still a very useful tool for reasoning.
I mean, I was trying to see if I can make some sense. I may not make any sense, but here's the thought, right? Would it help to remember that for matroids, the greedy algorithm works?
Yes.
And the proof goes by looking at exactly this remainder.
Yes.
And are you trying in some way to capture some part of that proof?
Yes, definitely, yeah. Yeah, so there'll be roughly one slide about that near the end, but that's exactly where these definitions come from, yeah.
Can you go back a slide?
Yes.
So this intuition about the remainder being the top and then the costs are next, this isn't true if H is like a set of high distributed elements and everything else is low distributed.
So yeah, so just remember again that this opt is taken after you sample the values, then you learn what opt is, right? And okay, let me rephrase. So let me say, like, for K-uniform matroids, you are allowed to have 2 copies of Charmander. That's fine. That really it's just K, you know, like multi-sets of size less than K are feasible, if that helps. Does that clarify your question? So if H is a set of highly distributed elements, they can be their own cost and remainder. That's fine.
Okay, so then the cost would be higher than the remainder.
No, you can be your own remainder. That's fine. I'm saying for a K-uniform matroid, I'm not adding a constraint that says you can also only have 1 Bulbasaur. I'm just saying you can have K secretaries. Yeah. Did that answer your question? Yeah.
So just to clarify, you said that this is a way also to study the competitive ratio of the optimal policy?
Correct.
Is that true? Is that obvious that we can achieve the best competitive ratio with those strategies, or this is something that will follow from?
So for one uniform matroid, well, for one uniform matroids, yes. For arbitrary matroids, also yes, because it turns out that thresholds like this can get you a 2 approximation, and you can't do better than 2 for matroids because you already can't do better than 2 for a single choice. Okay, so maybe a better question is for K-uniform matroids, I don't think you can do better than a constant with an approach like this, but you can, as K grows, get a ratio that approaches 1 for K-uniform. So that's maybe a good example that separates the difference.
We already pay a price even just back.
Correct, yeah. Okay. Okay, so let me now say, okay, so now I spent all this time giving you a definition. Let me at least use it for a theorem. So what we know is that if a thresholding algorithm has alpha balanced thresholds from this definition, then it guarantees a 1/alpha fraction of the expected opt. Sorry, it gets a 1/alpha fraction of the expected opt. Okay, so I'm not going to give you a complete proof of this, but I will give you an overview that captures the salient ideas. Okay, so what we can do is we can write the expected value of opt in the following way. We can just take opt and partition it into the cost and remainder. Okay, and this is fine because cost and remainder always partition opt. Even if h itself is a random variable, for any choice of h, this is just a partition of opt. Okay, and this not too small guarantee immediately tells us that just the expected sum of thresholds from what we hire gets a 1/alpha fraction of the expected cost. Okay, because this is just reading off the definition of not too small. Okay, so this is where it takes a little bit of work to see this. There's no way you can get this just by reading the not too big guarantee, but it turns out that the not too big also guarantees that the expected surplus, wi minus ti, for the elements we accept, gets at least a 1/alpha fraction of the remainder. Okay, and now when you sum both of these together, it directly tells you that the expected sum of weights gets you the expected opt over alpha. Okay? Okay, so this proves that coming up with balanced thresholds is useful. Now let's see if we can come up with some. Okay, so, hold on, what's going on here? Okay, sorry, okay, good, that is what I wanted to do. So let's observe that this threshold we used earlier for one uniform matroids is actually 2 balanced. Okay, so this is definitely a bigger hammer than we need to get a 2 approximation for one uniform matroids, but let's go through this anyway. Okay, so let's see if we can verify this. So if we hire anything, the threshold we use to hire it is exactly t, the expected max over 2. And what's the expected cost of a set of size 1? Was just the expected max weight element. Okay, and the expected weight of the max weight element is exactly twice our threshold. So this immediately gives us the not too small guarantee. Okay, now let's reason about the thresholds not being too big. So if we don't accept anything, what are the v that we can possibly add and still be feasible? It's any set of size 1. What is the threshold that we would have used to reject the element in v? It's exactly this. And what's the expected remainder of the empty set? It's exactly the expected max, which is twice our threshold. Okay, so if we accept nothing, then the sum of this sum of thresholds will be exactly t, and this will be exactly 2t over 2, which is also t. So it's good. If instead we accept something, then the only v we can add and still be feasible is the empty set. So the sum of thresholds will be 0, and the expected remainder will also be 0. Okay, so you immediately get not too big as well. Okay, so now rather than just reprove what we did earlier, let me show you that for k uniform matroids, you can also get 2 balanced thresholds. Okay, so the threshold we're going to use is the following. So for every element, we'll look at the expected opt divided by 2k, okay, where k is the rank. Okay, so again, to prove that these thresholds are 2 balanced, so it'll fit all on one slide. So let's think, so what is the remainder of h? We already went through this, so this is the highest weight k minus h elements. And what is the cost? It's the h lowest weight items in the top k. So what does this mean? So this means that the expected remainder of h is at least this. So what is this? So the expected opt over k, this is the average weight of an element in opt. And because the remainder is the top k minus h elements, all of the average weight here will be at least as large as the average. And there are k minus h of them. What about the expected cost? We can use the same reasoning. The average weight of an element in opt is opt over k. There are h elements, and they're on average going to be lower than the average. Okay, so we get both of these inequalities. Okay, so now let's see if we can prove that the thresholds are not too small. So if we sum the thresholds for everything we accept, we're going to get the following. We accept h elements. Each threshold is the expected opt over 2k. And immediately reading off what we have here, we get that this is at least the expected cost over 2. So this tells you that the thresholds are not too small. Similarly, if we look at any set of size v that we could have added to h and still been feasible, the maximum size is k minus h. Okay, and what's the threshold that we would have used to reject? It's exactly the expected opt over 2k. So the sum of thresholds for any feasible set we could have added is k minus h times the expected opt over 2k, which by here is upper bounded by the expected remainder over 2. Okay, so it directly says that the thresholds are not too big either. Okay, so this is a complete proof that these thresholds are 2 balanced, and plugging into the previous theorem, this would give you a 2 approximation for k uniform matroids as well.
Again, I'm still confused. If H is if you have a set of highly distributed elements, then your threshold, how is this balanced? Because they can't be their own remainder.
So let me just assert that define the remainder so that you can be in your own remainder.
Then what's the cost if that's the remainder?
So, okay, so formally, let's say that you have a 2 uniform matroid, and there's one element that has a very high distribution, and it's normally in the max weight basis. Then for this element, the remainder is almost certainly going to be itself, and the cost would be the other element of the max weight basis. So if you want a multiset with at most k elements, you would still kick something out of opt. It's not that you get to add yourself for free. You still count twice towards the k. Does that?
Yeah.
Maybe let me just assert that this is really the definition that you want. So if the more general definition I gave is confusing, really, I mean, when I say remainder of H for K uniform matroids, I mean the expected weight of the highest K minus H element. So just stick with this definition, and if the previous one is confusing, forget about it. Yeah.
So this algorithm or technique does not use the order of the
This also does not use the order, correct. Yeah. You do not need to assume that you know the order. That's correct. So actually, now that enough people have said it, so I think none of the algorithms that we'll see in this talk actually use that you know the order. Let me just say that. There's maybe like a subtle asterisk after that, but that's mostly true. Okay, so now, before I go on to general matroids, I want to prove the same theorem again, just to illustrate a technique, not for any other reason. Okay, so what I want to do is show you how you can prove that adaptive thresholds are balanced. Okay, so all we saw so far was that if the thresholds are fixed ahead of time, then how to show that they're balanced, but let's see how to do that for adaptive thresholds as well. Okay, so here's one way to set adaptive thresholds. Let me parse this first. So first, this opt sub C is going to denote the expected weight of the cth highest element. Okay, so op sub 1 is the expected max weight element, op sub 2 is the expected second highest, etc. And I'll use this h sub I minus 1 is the set of secretaries that you hired from the first I minus 1. So what is this threshold? It's basically saying, while you have accepted nothing, then the expected value of op sub k over 2, that's your threshold. And as soon as you accept something, the threshold goes up a little bit. Now it goes up to the expected value of op sub k minus 1 over 2. And when you accept k, L things, it'll go up to op sub k minus L over 2. Okay, so the thresholds are adaptive depending on the weights that come earlier. Yeah.
So opt is calculated on all the, you draw fresh samples and calculate it on all the secretaries, including the ones you have.
Correct, correct. That's right. Yeah. Okay, so let's try and prove that these adaptive thresholds are too balanced. Okay, so again, let's remember the remainder is the highest weight k minus h elements, and the cost are the lowest h elements from the top k. Okay, so the expected remainder, so now instead of just bounding it, let's write out exactly what it is. It's just the sum from c equals 1 to k minus h of the expectation of op c. Okay, because those are the elements that are contained in the remainder. Okay, and what is the cost? Well, let's do the same thing. I just chose to write it in a little bit of a funny way, but again, it's just summing everything that's not included in this sum, but is in opt. So just summing from c equals 0 to h minus 1 of opt sub k minus c. Okay, so now let's try and reason that these thresholds are balanced. So first we'll try and show they're not too small. So let's sum the thresholds for any set we accept. So what are the thresholds going to be? Well, we said for the first thing we accept, the threshold is op sub k, the expected value of op sub k over 2. For the second one, it's op sub k minus 1 over 2. For the third one, it's op sub k minus 2 over 2, and so on. So the sum of thresholds that we used to accept these elements is exactly this. It sums from c equals 0 to h minus 1 of op sub k minus c over 2. And that happens to be exactly the expected cost. Okay, let's try and show that the thresholds are not too big. So let's take any set of size that we could have added to h and still been feasible. So that set has size at most k minus h. How big could the thresholds have possibly been when we chose to reject them? Well, it's definitely not larger than the expected value of op sub k minus h, but maybe it was even smaller if the elements came earlier in the algorithm. And so what that means is that the sum of thresholds for any set we could add to h and still been feasible is at most k minus h times the expected op sub k minus h over 2. And this is upper bounded by the expected remainder over 2, because this is k minus h terms that are all op sub k minus h, and this is k minus h terms that are all at least that big. Okay, so again, this is just to show you a technique, how you can prove that adaptive thresholds are balanced as well. Okay, so the last thing I'm going to do is I'm just going to state for you the right balance thresholds to use for general matroids. I'm not going to give a proof that these thresholds work because that's a little too much for the talk. Okay, so here's the thresholds you should use, and these happen to be too balanced for all matroids. Okay, so what is this? This term, okay, so hi minus 1 are the secretaries that you've already hired when you process I. So this is the expected cost of h sub I minus 1 union I. So if you were to accept I, this would become your new cost, minus just the expected cost of if you didn't accept I, all divided by 2. So this is kind of like the expected marginal cost of adding element I to what you have so far, at least according to this specific definition of cost. Okay, so like I said, I'm not going to prove that these work. I will just give you some intuition as to where do these thresholds come from. Okay, so let's imagine two worlds. In world A, all of the weights are going to be redrawn fresh. The game is going to be restarted, except you've already hired secretaries hi minus 1. And so this limits the secretaries that you can hire because they have to be feasible when you add them to hi minus 1. Okay, in world B, same thing. All weights are redrawn fresh. The game is restarted, but now you've already hired secretaries hi minus 1 union I. So you're even further restricted on who you can hire. Okay, so very clearly world A is better. And it's not obvious how to see this from the definition of cost, but the definition happens to capture exactly that if you are a profit, then world A is better by exactly the expected marginal cost of adding I to hi minus 1. Okay, so just intuitively what that kind of means is that in order for you to prefer entering world B, Wi should be competitive with its expected marginal cost. And there's no good intuition for why dividing by 2 is a good idea. That's what makes the math work out. Okay? So does this make sense? This is just some intuition for why these thresholds work, and I'm claiming that they get a 2 approximation for all matroids.
For general matroids, is there a non-adaptive true balanced thing or not?
Let me think. For general matroids, there is no uniform threshold that gets a constant factor approximation. I do not know if there is a non-adaptive but asymmetric thresholds. I definitely don't know that they exist. I also don't know that they've been ruled out. Yeah. Okay, so that's the end of everything technical. Let's just recap what we saw so far in the whole talk. Okay, so I tried to just hammer in this concept of balanced thresholds. And the main idea was that you wanted to say that the thresholds were not too small, so that the thresholds themselves cover some fraction of opt, but also the thresholds were not too big, so that the expected surplus beyond the thresholds was also large. Okay, and I want to point out that there are different ways to reason about balanced thresholds. And so another one, here's intuitively what they would sound like, is you would like thresholds to be not too small so that you're unlikely to block any specific element from being infeasible to accept. But you'd also like them to be not too big so that you accept enough elements in expectation. Okay, right? So if you have thresholds that are very small and you just accept a lot of things right away, then many elements, they're never going to be feasible for you to accept. So this seems like a bad idea. But also if your thresholds are so large that you just don't accept anything most of the time, then this also seems like a bad idea. So there is a way to formally reason about this too. I don't have time to discuss more of this connection. I'll just point out that there's a tool called online contention resolution schemes, and this kind of reasoning is very related to this. Okay, and just to be clear, I'm not claiming that all proofs related to profit inequalities follow this methodology. And in fact, we know for K-uniform matroids, this methodology I don't think will give you the optimal competitive ratio. But I do think it's a good way to think about the challenge of profit inequalities. Okay, it's trying to come up with thresholds that are not too big and not too small. Okay, and the last thing I want to do is just very quickly survey some results in slightly different models. So what if you get to choose the order of the elements instead of having the adversary choose the order? Then you can actually improve the 2 approximation to e over e minus 1. And this is due to a result of Yan from 11. And I will state the algorithm, but I will not say anything about the proof other than this one sentence. Okay, so what the algorithm does is it just computes for every element what is the probability that you are in the max weight basis. And then it finds a threshold such that the probability that you exceed that threshold is exactly this Qi. Okay, then you sort the elements in decreasing order of Ti. So this is why you need to be able to choose the ordering. And then you just hire every secretary that's feasible subject to being larger than its threshold. Okay, and like I said, so all I'm going to say about the proof is just to give you this buzzword that the main tool used are called correlation gap inequalities.
What is known about random order?
Great, good question. So if if instead the order is random, then we know that for the single choice problem, so for one uniform matroids, you can also improve the 2 to an e over e minus 1. But we don't know beyond the single choice problem yet for random order, but with distributions. Okay, another question. So maybe this was a little bit subtle and I slipped it past you, but if you wanted to use the thresholds for the matroid profit inequality, you do need to compute some pretty intense expectations every time you process a new element. Okay, so and this is certainly possible to do if you have the right access to the distributions, but a reasonable question to ask is what if you don't have the right access and you only get access to samples? Okay, so we do know that for k-uniform matroids with only one sample from each distribution, you can still get an asymptotically optimal algorithm, but this is just a cute question that I don't know the answer to, which is what is the best competitive ratio you can get for the one uniform problem with one sample from each distribution? Okay, so all I know is that a reasonable thing to do is to set the highest element you see in your samples as a threshold, and it's not too hard to show that this gets a 4 approximation. With some more work, you can show it does better than 4, but I don't know what the what ratio exactly this algorithm gets or if there's anything more clever. And definitely, I have no idea how to get a constant factor approximation for all matroids with just a single sample from each distribution. Okay. Okay, one last comment. So what if an adversary adaptively chooses the ordering? So what if it's more powerful than what we saw on the last slide? So basically, every result in this talk holds, even if the adversary knows the weights exactly. So if the adversary is a prophet, it knows exactly the weights and then gets to mess with your algorithm. The exception is, again, the matroid profit inequality, which does hold against adaptive adversaries, but not quite so powerful. So if the adversary is adaptive, but it doesn't know the future, then the matroid profit inequality holds, but we don't know if it holds against this prophet adversary. Okay, and last comment is one of the reasons that our community has been doing a ton of work on multiple choice profit inequalities in the last few years is because there's kind of a generic reduction from designing good profit inequalities against appropriate adversaries, and these immediately imply good mechanisms in certain Bayesian settings. And I think Anna is going to talk on Friday more about this. Okay, so this is everything I have for the first half. Thanks a lot for listening.
So for the random order, I think for the matroid one, we have something better than 2. We still, but I mean, not one even like 1 over u or the inverse of that, but something slightly better than 2. I think it should be.
Okay.
And also another thing is that, I mean, another nice problem you can say about the profit secretary, like profit inequalities, minimization version of this problem. Because you try to maximize the things. I mean, you can't just do exactly all of this minimization. And here in the same paper, we show that actually lots of minimization, at least the natural version does not work. You may need to change.
So you mean minimization, but you're forced to accept something.
Yeah, I mean, you need to choose one essentially, such that you minimize the things. You have some certain properties. So that's another thing that. Yeah.
Cool. Yeah, so I also didn't mean to say that this is an exhaustive list of other problems related to profit inequalities that are studied. So that's a good one too, the minimization.
Another question.
Yeah.
Is this bound e over e minus 1 tight or?
So that's a good question. I was actually, so I thought it was tight. Someone caught me like right before the talk and told me that they think it's not tight. So it is tight for the correlation gap inequality. So the proof technique can provably the proof technique is not going to get better than E over E minus 1. But I'm not positive that that for this problem, E over E minus 1 is tight.
Okay, last question.
So I missed the discussion there. So for a general matroid, if you have non-adaptive thresholds, can you get constant, or you said you cannot?
So it's I don't know. I also don't know that they've been ruled out. So I do know that with a uniform threshold, you cannot get a constant factor approximation. But maybe with non-adaptive but asymmetric thresholds, you can. I just don't know how to do it, and I also don't know that it's been ruled out.
Okay, we'll continue at 3 p.m. Okay.